and then we're looking at f of 2. How do you use a graph to evaluate f of -1? What does that mean you're supposed to look at, Emma? Yeah, so the number in parentheses always represents your independent variable. That's your x. So in your graph, if x is -1, what's the corresponding point? Emma, if x is -1, what's the corresponding y value? -5. So here is where x is -1. The value that corresponds with it, here's that point. Well, we need the y of it because we know x. So that you're finding its matching y coordinate. So then at f of 2, Emma, the y value is 4. So right here is the point in the graph. My x value is 2. Its attached y value is positive 3, maybe? Is mine 3 and yours 4? Yours?
Yes.
Yours is 4. Mine says 3. Okay. I need to change my little curve there a little bit. And then the last question says, what is the range? So your range is going to be different than the graph that I have here. Let's see if I can change mine. There we go. Good. So what would the range be of the graph? Yeah. So starts down at -5, it goes up to the max, the highest point of 4. So when you're doing range, you're doing that vertical distance the graph is traveling. So it's starting at vertically at -4, its highest point. It doesn't matter that it ends at 0, it's all of the distance that it's covering vertically. Questions? So before I go to the next problem, just from your homework, let me grab the right homework assignment, 60. If you can look at number 60. Number 60 gives you the function, the 4th root of x squared plus 3x, and they're saying it's greater than or equal to 0. Any even root. I think I added that greater than or equal to 0 because that's in my problem when I was doing it. Any even root, a 4th root, a square root, a 6th root, a 10th root, whatever is underneath the radical has to be greater than or equal to 0. You cannot take the 4th root of a negative number. You can't take the 10th root of a negative number. So when you're solving for radicals and it is an even power, whatever's underneath that radical has to be greater than or equal to 0. And that's for any even power. An odd power, it doesn't matter. So if it was the cube root of something, that's allowed to happen because I can take the cube root of a negative number. I can take the cube root of a positive number. So if you're solving for this, to get rid of the 4th root, you would raise it to the 4th power. That's how you get rid of the radical. And then we have x squared plus 3x is greater than or equal to 0. How would you find the values that would work? Like, what would you do here? Emma. Yeah, we gotta factor it. So what would you pull out, Emma? An x, and then I get that x plus 3. So if I'm thinking about on a number line, one of the values is going to be at 0 because x is by itself. A second value is going to be at -3 because if I just look at this spot here and get that value by itself, I have the value of -3. So if I plug in a -3, -3 squared is 9, plus 3 times -3, that gives me 0. I can take the square root of 0. But then anything less than that might not work. So now I have this like number line with these intervals again. So this was similar to what we did in the previous chapter because I have 1, 2, 3 different intervals that could be the solution. So I need to check to see what would be part of the solution. Where does the domain exist? So can I plug in a number like -4? Could I plug in a number like -1? Or could I plug in a number of 2? So would those values work? And if I plug in a -4, Colin, -4 squared is?
16.
And then plus 3 times -4 is 4. Can you take the square root of a positive number? Yes. So anything less than -3 works. But if you plug in a -1, -1 squared is 1, plus 3 times -1 is the square root of -2. So the numbers between -3 and 0 do not work, because that is going to make our radical negative. And then just checking, if I plug in a 2, 2 squared is 4, plus 3 times 2 gives me the square root of 10, so that also works. So when you have a polynomial, a quadratic, that you're solving for and you're trying to find the domain, it's not just -infinity to -3, -3 to 0, 0 to infinity, because it's under a radical. We're trying to figure out when that radical is greater than or equal to 0. Not that it's undefined anywhere, but we need to figure out where is it greater than or equal to 0. So this would be from -infinity to -3. -3 is allowed to exist because you can take the square root of 0. And then from 0 to positive infinity, any of those numbers also are allowed to exist, because that remains positive underneath the radical. So when you have to factor something and you get multiple values, like you really do need to think about that number line and what values it creates on the number line and how those are working. So it's not just a quick like, oh, it must just be from -infinity to -3, -3 to 0, 0 to infinity. So especially that like case pertains to a radical, a square root. And that kind of goes back to the last chapter when we were looking at those inequality polynomial functions. Questions? So I wanted to make sure we kind of talked about that one a little bit. The answers I put on Google Classroom after school yesterday. I also sent them through Remind. The back of the book does not use interval notation, so please make sure you're checking your answers. 84 and 86 were also completely worked out for you. 85 was like 84, like 86. So 85 and 86 were similar because they were fractions. 85 I think was a little easier. Questions? So we're going to go through the rest of section 1 through today, which you'll need a calculator because we're going to use it a little bit. But this is all on graphing pretty much. So looking at the graph and trying to evaluate the graph. Whereas section 1-2 was finding information algebraically by relying on the equation and the function. So you can always rely on a graph, but we like to use that equation as well, so that we're trying to use the algebra behind it and not just what the graph is doing. Tomorrow we will kind of review domain and range. And we'll review piecewise functions. We will review not interval notation. We'll review that difference quotient. We'll review evaluating functions. So we'll kind of go over a little review tomorrow, sections 1, 2, and 1, 3. So we went through the first example with our graph. Underneath it, it reminds you about the vertical line test. Does anybody remember what the vertical line test does, Colin?
It's where if you draw a vertical line on a graph and it touches more than one point, it's not a function.
Right. So we talked about something being a function if each input has exactly one output or each x has one y. That's the algebra part. So algebraically, you're looking at your x and y values. Does each x have one y? But the vertical line test works graphically. So if I have a graph, so each vertical line can only cross through the graph once for it to be a function. You could also have the flip for that. If a vertical line crosses through your graph more than once, it's not a function. So So write something there to remind yourself it's a test to see if a graph is a function. It is a function if each vertical line only crosses through your graph once. It's not a function when your vertical line crosses through the graph more than once, because then you have two y values corresponding to one x, and that means it's not a function algebraically or graphically. So the vertical line test is a test that we use to decide if something is a function. We'll also talk about the horizontal line test as well. So that goes along with inverses, and we'll get to that at the end of this chapter. The next thing underneath there, I think, is increasing and decreasing functions. So we're really going to analyze a graph. Not only are we going to look at the domain and the range, but we're also going to look at where is a graph increasing or where is it decreasing. So if you have a function, and let's see here, let me just make it something that looks like this. When you read a graph, how do you look at a graph? How do you describe a graph? Colin? From left to right. So when you're looking at the graph and you're deciding the part that decreases or increases, you're looking at the movement starting on the left, just like you do a book, and moving to the right. So even though this little left side here has an arrow pointing up, it actually is the part that is going down or the part that is decreasing. So from left to right, that slope of the line is going down and it's decreasing. So that would be our decreasing portion of the graph. The part in the middle, it's supposed to be horizontal line. What do you call that if you have a horizontal line? Yeah, that part's constant. Because it isn't moving, it's just flat horizontal. It has a slope of 0. So we actually call that part constant. And then the other part is going upward from left to right, and that's our increasing part. So an increasing function goes up from left to right. The decreasing portion of the function goes down from left to right. The function can do multiple things. So this actually does all three possible options besides the part where we go vertically. But we have the decreasing part, we have a constant part, we have an increasing part. We are going to be describing these. I can spell. We're going to be describing the increasing or decreasing intervals using the x or the horizontal distance. So I might be looking up and down because something is going up or going down, but we're going to be describing them as intervals using the horizontal distance or the x. So a question will say, where on the graph is the function increasing? And we're going to locate that we're going to find that location on the graph, but we're going to describe that using the horizontal distance that it's taking up on the graph. So if you look at the picture underneath, it says find the intervals on the graph that are increasing or decreasing. And I hope my graph is like yours this time. So we should have a point at 1, -1, 2, and 1, -2. You guys have those 2 points. It goes down the same. Yes. Okay. So if we're reading the graph from left and right, Lauren, how many increasing intervals are in this graph? 2. So the part on the left is increasing. So here's an increasing interval. The part on the right is also increasing. So there are 2 increasing intervals. You're asked to find those intervals, which really means we're going to describe that distance that it's increasing. So how far from the left to the right is it actually increasing? So I located them, kind of labeled them, but now we're actually going to describe that distance. So we'll start with the increasing intervals. Because there are 2 sections of the graph that increases, we're going to have 2 intervals that increase. So Carrie, if you look at the part on the left, giving me the x, so the space horizontally that is increasing, how would you describe that section on the left of the graph?
starts at -5 and ends at -1.
So I agree with the ends at -1. And you said it starts at -5. If this
Oh,
continues
it's
to
negative.
right, so even though it's going down, it's continuing to stretch horizontally forever to negative infinity. So it's going to start increasing at negative infinity, whatever that number is, and it's going to continue to increase until it hits the x value of -1. So I know you're saying, yeah, but it goes to the height of 2, but we're not worried about its height. We're describing this horizontal distance where it's increasing. So that would be from negative infinity and then to -1. Negative infinity gets a parenthesis. The 1 also gets a parenthesis, the -1. And that's because that's called a changing point of the graph. It's our maximum point or our minimum point. So it's an inflection point that is going to change from being increasing to decreasing, and it can't do both. So it stops increasing right before it gets to the highest point because the max is kind of separate. That's a separate point in itself. So the next increasing value, I'm going to put a little union because there's a second increasing value. Brenton, can you tell me the other part of the graph that's also increasing? So that piece on the right.
It's starts at -2.
So that would be the y value. That's okay, it's hard.
It's 1,
1, yep,
and it goes to +.
and it goes to positive infinity. Nice job. And again, that gets a parenthesis because that is our lowest point of the graph. It's the minimum value, and it's going to increase and decrease there because they're kind of like meeting at a point. So we always use parentheses. We don't include that number in the uniform. Questions? It's tricky to look vertically, but explain horizontally. Because like you are looking up and down, because it's increasing up and down, but you're explaining the horizontal distance. So then the other piece in the middle would be the decreasing part. How would you describe that little middle distance between those two values horizontally that is going down? Josh?
Parentheses -1. Constant.
Yeah. It's just the in-between numbers, pretty much. What's in between the increasing section? Well, that would be from -1 to 1. That's where it's going down. And again, it gets parentheses. So the maximum point, the minimum point, those are called turning points, inflection points. And they're always going to just be the parenthesis values. So it gets up until really close to that point. But the highest point of the graph is kind of like where it changes directions. Questions? So I believe that takes us into then another vocab term underneath where it says a relative max and a relative min. So again, we're going to draw a little picture. The true max or min of this graph, I have true max at infinity because that's where it goes. It goes up to positive infinity. However, a relative max is the lowest point or the highest point of the graph with respect to the points that are around it. So right here, this is called a relative max. It's the highest point with respect to the ones that are around it. It's the top of the hill. There are two relative mins, and that's again with respect to the lowest points that are around them. So it's lower than any point that is around it. So there are two relative mins in this graph because they are the lowest points compared to all the points that are around it. So there's not just necessarily one max or one min. I could have a whole bunch of maxes and min values. So the mins are in the valley, the maxes are at the top of the hill. And you probably won't always see that word relative, because that word just kind of gets dropped off often. So, it gets left off. It might just say find the max and the min. But really, we're still finding that top of the hill or the bottom of the valley. So I think the next question asks you to use your calculator. So if you want to plug in, it's at the top of the next page. Use the graphing calculator to find the relative max and min values of the function. And we have -x cubed plus x. So plug this in your calculator, get yourself a little graph to look at. draw yourself a little sketch. So if you look at your graph, it's kind of hard to see if it has a max or a min, but I can see on the left that it goes a little bit under the x-axis, and on the right it goes a little above. How can you get a better view with the calculator to kind of see what's going on there? You can trace it, so that would be one thing. How else could you get a better view of the calculator so that you have something like a little clearer to look at, so you can see where that top part is or where the bottom part is? You can zoom in. So I'm actually going to use that option. So literally, if you hit zoom, number 2, it zooms in to the center of the graph so that you can see a little more clearly what's going on with the graph. And then you can actually see the curve, the relative min, and you can see the relative max. So by using that zoom in feature, sometimes it helps to zoom in on the graph so that you can truly see where that is happening. Does anybody remember how to use the calculator to find the max or the min? Dylan, where do you get that at? Yeah, whichever one you happen to find. So when you go to second calc, there are a whole bunch of options under there. So we've used the intersection option. We can use the value button if I'm trying to find a value for x. We could find a 0, but min or max is what we're looking for. So if you hit the min button, you need to arrow over that little cursor. The left bound means it needs to be on the left side of the minimum location. So my minimum location is somewhere around here. I need to make sure I'm slightly left of it. And then you hit the enter. The right bound means I just need to be somewhere to the right of the lowest point, because we're kind of getting those values that are surrounding the lowest point in the calculator. And then hit enter, never do anything for guess. So it tells me that the minimum value is negative 0.58 and negative 0.38. So that's where the lowest point of the graph is, the relative min. And that's the lowest point of the numbers that are surrounding it. See if you can find the max as well if you haven't done so already. So use second trace. The right bound means you need to be on the right side of the peak. The left bound means you need to be on the left side. We use max and mins to help us describe those intervals where the graph is increasing or decreasing. So that's why we use max and min values, because it stops increasing or decreasing at the max or min of the graph. So Colin, the max of the graph is at?
5.57 and then 0.38.
Yeah, I think it rounds up. Questions? Draw yourself a little graph. So if I was describing my decreasing section, I would be looking at this section here. It stops decreasing at the minimum location. Or here's another decreasing section. So it starts decreasing at the maximum and then it continues on. Questions? So the last concept of using graphs, talking about things being even and odd. Numbers are even and odd. I actually like odd numbers better than even numbers. And I set my clock for 4:59 every morning because I don't like waking up at an even number. I don't know, it's like a superstition. Who knows why? But I feel better when I wake up on the odd number. So 4:51:9 is the time that my clock is set every morning. So functions are also even or odd or neither. So numbers can't be neither besides 0. Because 0 you could say really isn't even or odd. It's 0. Some might argue one way or the other. But a function is even if it has y-axis symmetry. So even functions are determined graphically by looking to see what type of symmetry they have. What type of graph would have y-axis symmetry? So think of a graph. What would it mean if it has y-axis symmetry? What's symmetry mean? The same. So what graph would have y-axis symmetry, where the same thing on the left and the right? Garrett?
Parabola.
Yeah, a parabola. So if I had a parabola, nice job, Garrett, anywhere where the vertex is on the y-axis, it has y-axis symmetry. And that's also, if I drew a good parabola here, doesn't look like I drew a nice one. My x value and y value on one side should match up with the same x value and y value on the other side, but the x value is going to be negative. So if I have the same vertical value on the left and the right, the x is positive versus negative, that's y-axis symmetry. So even functions are symmetrical about the y-axis. There aren't going to be many of them. So a parabola is only an even function when the vertex is on the y-axis. Odd functions have what we call original symmetry. And this one, if you remember odd and origin, they both begin with 0 or an O, not a 0. An O, that's the easiest way to remember. Odd has original symmetry. This one has to go through the origin, or at least the origin has to show the symmetry of it. So a graph that might go through the origin would be kind of similar to the one that we just looked at. Would be some kind of maybe cube function. So the opposite quadrants should be identical to each other. So kind of across the origin. Quadrant 2 and quadrant 4 should look the same. Quadrant 1 and quadrant 3 should look the same. And then it does kind of go through that origin to have original symmetry. The last one would have no symmetry. So if it's neither, it doesn't have symmetry. And that's pretty much a lot of graphs. So there are only a handful of graphs that might be even or odd. Most graphs are going to be neither. So draw any graph that doesn't have symmetry with the y-axis or with the origin. So sure, it could have symmetry about its axis of symmetry, but there's really only two types of symmetry that we would focus on, and that would be even versus odd, y-axis versus original axis, or original symmetry. So make your graph somewhere else, doesn't really matter where. So I have a parabola here. Yes, it has symmetry, but it doesn't have y-axis or original symmetry. Questions? So there are 2, 3 final problems at the bottom, and this is more algebraic. I guess I didn't get to my domain and range, the little worksheet that I passed out to you. So it says determine if the function is even, odd, or neither. So how could you determine if this was even, odd, or neither? What could you do? Nick, what are you doing? What could you do?
Find the x min and x max.
You could find the x min and x max. What else could you do? Brendan?
Just graph it and look at it.
Yeah, you can graph it and look at it. Don't even make it hard. Graph it and look at it. So if you plug this in your calculator,
Yes.
that lovely calculator that you have, does it have y-axis symmetry? Does it have original symmetry? Or it isn't either one of those options. So see if you can plug those 3 questions into your calculator. Or maybe you know what some of them look like without using the calculator. So Brenton, what do you think about A?
I think it's odd
Why is it odd?
because it makes that weird cube.
Yeah, it makes that weird,
Goes to the origin.
kind of goes through the origin, and it has that little curve min and max to it. So that first one is odd. And that first one is very similar to the one that we have above. It's just the flip of it to example 3. Letter B, that's a parabola. And it just moves up 1 on the axis. So this guy is even. Any parabola that's on the y-axis is even. And the last one, that one's neither. Because it starts down at -1. And the first quadrant is not the same as the third quadrant. So this is a neither option. So keep that little half sheet. We will talk about it tomorrow. So the receiver sheet is being packed.
Okay, so the flip side. I'm sorry, let's go see.
Anybody interested in doing 31 or 59 for me tomorrow? No.
Oh wait, I'll do 59.
You'll do 59, I'm on 31? Yeah, awesome, thank you.